Okay, let's get started. So welcome everyone to another lecture in our ID 5130 parallel scientific computing course. So in the last lecture we looked at four methods, essentially four different methods for in the numerical methods for in OpenMP programming. We looked at the matrix addition, matrix multiplication, as well as explicit finite differences and implicit finite differences, right? Implicit spatial finite differences. So as part of that, we noted that if you use let's say something known as the implicit finite differences or PADE or compact schemes, you essentially end up with a system of linear equations which seems to be not very straightforward to solve, right? Because you would have to solve the system to get the value of derivatives at all the points in one go. Okay, so let us, in today's lecture, let us kind of explore more on this one. So we also noted that use of such implicit schemes resulted in something known as tridiagonal systems, okay, or tridiagonal matrix systems, right? So what we mean by tridiagonal is basically if you have a matrix A which has, you know, elements A sub ij, where I comma j belong to 1, 2, 3 all the way to n, it's called a, I mean, you know, this matrix Aij is called a banded matrix or a tridiagonal matrix. First let us look at banded matrix. Banded matrix, if essentially when Aij is equal to 0 for essentially once you kind of go outside some bandwidth, okay, some r is the semi bandwidth. So for I minus j, modulus of I minus j greater than r, if the elements of the matrix are 0, then it is called a banded matrix, and if r is equal to 1, what you get is basically a tridiagonal matrix. Okay, so what is a tridiagonal matrix? Essentially you have only non-zero elements, in the principal or main diagonal and super and sub diagonals, right? That's a tridiagonal matrix. Now of course there are several solution methods available. Some of them are, I mean, those that are tailored for calculation of banded matrices are essentially, there is a Gaussian elimination which works for both regular dense matrices as well as banded matrices, as well as you have LU decomposition, and of course there is also something known as Thomas algorithm, or something that is also known as tridiagonal matrix algorithm. This is called TDMA. Okay, all right, so there are all these methods, but then all of them basically rely on the pretty much the same principle. Okay, so we are going to see, let us say we're going to see how LU decomposition works for tridiagonal, for the solution of tridiagonal matrices. So as an example, let us consider a matrix A that is basically given by B1, B2, B3 all the way to Bn minus 1 and Bn. So Bn are your Bi are your diagonal elements, on the diagonal, and we have the super diagonal elements, that is C1, C2, C3 all the way to Cn minus 1, and then we have, after C we have all zeros, right? And then similarly for the subdiagonal elements we have A2. Here 1, 2, 3, all these indicates the corresponding row, right? So basically we have B, C coming in the first row are B1, C1. In the second row we have A2, B2, C2. Similarly we have 0, A3, B3 all the way. Then we have Bn and An, and then you have in the n-1 row you have An-1, Bn-1 and Cn-1. Otherwise everything else is 0, right? So basically you only have elements along the primary diagonal and on the super and the sub diagonals. Okay, so we have these three diagonals. That's why it's a tridiagonal matrix as we know it. Okay, now of course in LU decomposition what you do is you express your matrix A into a product of two matrices. One is the first one is known as L. This is basically a lower triangular matrix, right? Or a matrix, basically a lower triangular matrix we can say, but in this particular case it is actually a lower triangular branded matrix, and then we have this one is basically an upper triangular matrix. Okay, so by looking at the structure of the matrix A, we can actually be a little clever and say that okay, my L and U also should also be banded to get a pattern like this when you multiply them together. So as a result you can write L matrix as by taking ones on the diagonals. Okay, you basically make all the diagonal elements as 1, and then you would have only the lower elements, that is L2, L3 all the way to Ln, right? So L3 1, and then these are all zeros, right? So this is basically, and then everything else other than the sub diagonal is also 0. So that's your matrix L. And then you can also have an upper triangular matrix U because you have made the elements in the diagonal to be 1. It is necessary to make them 1, right? Otherwise you would have too many unknowns. So you can make them 1, and then you can leave, you can basically have to write what are the elements on the diagonal as U1, U2, U3, Un-1 and Un. That's the elements on the diagonal for the upper triangular matrix. And then you also have to of course make elements for the upper triangular matrix, that is basically for the zeros. I mean essentially here there were zeros, these will be untouched, and these will be like C1, C2 all the way to Cn-1. So what we see here is that because of this particular decomposition, here the C are already known, right? These are already there in the matrix A. Okay, so this you can verify. You can decompose like this. Of course you can also decompose in any other way, but then you will end up with this kind of pattern once you do that. Okay, so basically you multiply L with your matrix U to get elements in the matrix capital A, which is basically written here, right? Okay, so if I do a element by element multiplication, right, then that means if I multiply, let's say first row with the first column, right, I'm going to get U1 equals B1, right? I'm going to get, if I multiply U1 equals B1, right, because in the A matrix we have the first element is B1. Okay, similarly if I multiply the first row with the first column, of course you're going to C1 equals C1, so that is of no interest, right? If I multiply the second row with the first column, I'm going to get L2U1, right? So that is L2U1 equals, okay, multiply the second row with the first column, L2U1 equals is how much? Second row with first column, that is basically your A2, right? That's your element here, right? We're going to get this A2, so that is nothing but A2. Similarly, if I multiply second row with second column, I'm going to get L21 multiplied with C1 U2, so I'm going to L2 C1 plus U2, so L2 C1 plus U2 is going to give me second row second column, that's basically B2, right? It's going to give me this element B2. Okay, so that is that's your B2. Similarly, if you repeat the process for, let's say, third row with the second column and third column, then you're going to get L3 U2 equals A3, and then L3 C2 plus U3 equals B3. Now if you keep doing this for one or two more, you can actually write a general formula, right, in terms of for any row k, right? So that will be any row k plus 1. We have Lk plus 1 equals, I can write it as AK plus 1 upon, from here I can write it as UK. Okay, that's one. And then the second one is basically L is one unknown. So in this matrix, what are unknowns and what are knowns? Of course your matrix A is completely known, so A, B, C for all the indices are known. your unknowns are basically L and U, right? So you have only two unknowns, or rather two sets of unknowns, so you would need two sets of equations. So you have already one set of equation for L's. The other equation you can get from the second one, so that is this one. This is basically gives you, if you rearrange, UK plus 1 equals BK plus 1 minus LK plus 1 times CK. Okay, so basically we have these two equations, so equation 1 and equation 2. Okay, these two equations. Now once you solve for these two equations, you can actually get okay, so your initial UK is already known, right? U1 is known, so that can be used for starting this, right? For L2 and U2 and so on. Okay, U1 is known from here. All right, then once you solve these equations, you know completely the L and U matrices, right? The elements in L and U are completely known. Then you can go and recast your equation. Let's say if you were to solve AX equals let's say Y. Okay, so Y is the known right hand side vector, right? And then X is the unknown and A is the known matrix. Now A you're going to decompose as L times U times X equals Y. Then what you need to do is essentially you would write Ux equals some unknown Z, Lz equals Y. So on this, once you know all the elements of L is known, Z is an unknown, and then Y is known completely. So use the matrix L, and with this you can do a forward substitution. That means write forward substitution and calculate what is this right hand side and right at the left hand side vector Z1 Z2 all the way to Zn. That's your vector Z. Okay, so using forward substitution you can calculate what is the vector Z. Once you know the vector Z, you can solve for this Ux equals, keeping the right hand side as Z, you can solve for X. Okay, calculate X, which is X1 X2 all the way to Xn. Now Ux is basically an upper triangular matrix, so as a result you have to do a backward substitution because you have one element here and so on. So you would use backward substitution or backward substitution, and then calculate your X. So once that is done, you can calculate X. Now as you can see here we have what is the computational complexity of this algorithm. So essentially you have these equations here, which is basically runs for order n, right? So because this is order n, this is order n, total are order n, and then you have, of course, here you have order n and order n. So essentially the computational complexity is only so of the Gaussian elimination, which will also be very similar. So either Gaussian elimination or LU decomposition, right? LU decomposition, the computational complexity is order n. Okay, or even for the Thomas algorithm, you can show that all of them will come out to be the same order. Okay, but what is the shortcoming here? The shortcoming is that if you try to calculate this using a parallel program, then we are concerned with either loop carried or data dependencies, right? So if you go back, main thing here is that these two equations. So here, if you'd like to parallelize them, then you can see that there is a clear data dependency, for example, or loop carry dependency, because your LK plus 1 depends on UK. So unless UK is calculated, you cannot calculate LK plus 1, and then only if LK plus 1 is known, you can calculate UK plus 1. So there is a loop carry dependence between the iterations here, as well as a data dependence. So such a kind of dependence will basically restrict you from parallelizing this, right? So as a result, the Gaussian elimination or LU decomposition in this particular form can only be computed sequentially, right? And it is not suitable for parallel implementation. Okay, so then but it's all not so bad, because we will see later that even we can use this both for serial computation as well as for multidimensional parallel computation. Okay, so we will get back to that a little later, but as of now, in its own form, in this particular form, if you just have to parallelize this particular tridiagonal matrix in this particular form, is not suitable for parallel programming, owing to the loop carried as well as the data dependencies. Okay, so fine, so far so fine. So we have learned something which is of course useful, and we will see how to make it used for parallel programming as well. But before that, let us also see if there are any alternate algorithms that are already proposed in the literature, and if they are used, if they can be used for our computation. So there are two such algorithms. They are known as the I mean, there are many algorithms, but the most popular ones are known as the recursive doubling algorithm, as well as the other one is known as cyclic reduction algorithm. Both are basically can be thought of different implementations of the same idea proposed by Hockney and Golub back in 1960s. Okay, it's almost 60 years back. So these methods basically also work with elimination steps. So we didn't do actually Gaussian elimination, but essentially, if we had done a Gaussian elimination, the lower triangular matrix that we have built would have contained all the the operations that we would have taken care in the row-wise operations, and the U would have been the resulting matrix. Okay, so that's how to look at it in a different perspective when you want to connect the Gaussian elimination and the LU decomposition. Okay, so essentially these two methods are basically also contain elimination steps, but they are also they have this particular method have potential for parallelization, which was kind of absent in the regular tridiagonal matrix solution. Okay, so both these methods are of course only applicable if your matrix is a symmetric and positive definite, or in another terms, it is diagonally dominant. Okay, so if something is symmetric and positive definite, what does it mean? If a matrix is symmetric, that means its transpose should be equal to itself. That is a symmetric matrix. And something that is positive definite is if you have a variable x or a vector x, then x transpose times ax for any x greater than 0 should be positive. Okay, if this property is valid, then A is called a positive definite matrix, and this property makes A as a symmetric matrix. Okay, now diagonally dominant is just a different term for this. In diagonal dominance, what we say is that the absolute value of the diagonal element, the absolute value of the diagonal element should be greater than sum of all the values in that row. Okay, that means the diagonal element should be greater than sum of all the other elements in that particular row. Then that matrix is called a diagonally dominant matrix. So these are diagonal dominance is kind of very much required when you work with iterative methods, which we will go into it later for the solution of linear systems. As of now, we will kind of look at, assume that the matrices that we're going to work with are symmetric and positive definite or diagonally dominant, so that we can apply either of these methods, that is recursive doubling or cyclic reduction, for that particular system. Okay. So again, we work with, of course, a banded matrix, and let's say the matrix is again, or the system is in this form. You have Ax equal to y, so where y is the is a known right hand side and x is the unknown, and then this is the matrix. Okay. And then the structure of this matrix is again similar to what we had before. That means we had, for I equals 1, we have b1 x1 plus c1 x2 equals y1, and then we have a general equation is ai xi plus bi x I minus 1 plus ci xi plus 1 equals yi, where I goes from 2, 3 all the way to n minus 1, and then finally we have the last expression is basically a n x n minus 1 plus b n x n equals y n. Okay, so basically we have a matrix whose, when expanded, the system, the linear system equations read like this. Okay. Okay, so the whole idea is now is basically use the I minus 1th equation to eliminate xi minus 1, and use the I plus 1th equation to eliminate xi plus 1. Okay, so that is the whole idea. And then once you have expressions for xi minus 1 and xi plus 1, substitute them in the equation for xi. Okay, so essentially once you do this, your equation for xi, or substitute in the equation for I, okay, so that you will get an equation for a final equation would basically now contain xi, xi minus 2 and xi plus 2, okay, instead of xi minus 1, xi plus 1. Okay, now we will see how that is going to work. Okay, so but the idea is essentially once you do this kind of recursive doubling, what happens is that your coefficients values that you have on the sub or the super diagonals will be moved out by certain distance. Okay, now if you basically apply the same formula recursively, then these will be moved out and so on until they are kind of completely eliminated from the matrix itself. Okay, so that is the whole idea. So essentially the recursive doubling algorithm will repeat the same process of elimination for xi minus 1 and xi plus 1, and thereafter for xi minus 2 and xi plus 2, and so on, and xi minus 4 and xi plus 4, and so on, until you basically get just a matrix that is basically a diagonal matrix. Okay, essentially you don't have any other elements, everything else will be 0, and that is the idea of recursive doubling. Now in cyclic reduction is also very much same as recursive doubling, but what you do is you essentially basically half while you are doing these substitutions and removing the sub and super diagonal elements, you are also reducing only half the number of equations are solved. At any iteration or at any step. As a result, the computational overhead will be reduced, the computational cost will be reduced. However, unlike the recursive doubling, in cyclic reduction you don't end up with a kind of only a diagonal matrix. As a result, you would read a substitution step to calculate the unknown vector. Okay, we will see if time permits, we will look into cyclic reduction as well. Otherwise, we will only stop with recursive doubling, and then cyclic reduction will take it up maybe later on through an assignment or something like that. Okay, all right, or through a tutorial or something like that. All right, let us first look at the recursive doubling algorithm. Once this is clear, I think the cyclic reduction is very easy to understand. So recursive doubling. Okay, so So basically we have a coefficient matrix, right? So we have the coefficient matrix, we have Ax equals y, and the coefficient matrix A is basically given by what was in the diagonal? Diagonal is basically b1, b2, b3 all the way to bn minus 1 and bn, right? And our super diagonal elements are c1, c2, c3 all the way to cn minus 1, and these are all zeros, right? And then we have a1 or a2, a3 all the way to an minus 1 and an. Okay, so that's basically our matrix. Now let us consider the I minus 1th equation and the ith equation, okay, or I minus 1th and ith and I plus 1th equations, okay, that are coming out of this particular system. Okay, all right, so what is the I minus 1th equation? Okay, I'll leave it here. So just to be on safe or remote, to have a similar structure, I'm considering I to range from 3, 4 all the way to n minus 3 and minus 2. Okay, so I'm not going closer to the 1 and 2 as well as n and n minus 1, because the neighboring equations are here are only contain 2 coefficients, and then the equation for here also will contain, as a neighbor, this will only contain 2. So let me focus from 3 to n minus 2 elements here, and we will see what can be done for the other 2 boundary rows, and on both sides. So if I write this, if I write the I minus 1th equation, what will this be? This will basically be look like your ai, the coefficient will be a minus 1, and because you are writing equation for I minus 1, your x will be 1 lesser, so xi minus 2, plus you will have bi minus 1 xi minus 1, plus you will have ci minus 1 xi, right? That's what you will have. And then on the right hand side you will basically have yi minus 1. Okay, now similarly the ith equation would be, okay, so I'm kind of erasing this thing. So this is the, you understand that the first equation we have written here is the I minus 1th equation. Now I'm writing the ith equation. Ith equation would be ai xi minus 1, right, plus bi xi, right, plus you will have ci xi plus 1 equals yi, right? That's your ith equation. Now if I write the I plus 1th equation, it will be ai plus 1 xi plus bi plus 1 xi plus 1, plus I'll have ci plus 1 xi plus 2 equals yi plus 1. Okay, so that's your 3 equations. You have the I minus 1th equation, ith equation, and then we have the I plus 1th equation. Okay, so we have all these 3 equations. Now, as we discussed before, as we said before, the idea is to remove, let's call this different numbers. Okay, so this is equation, let's say I minus 1, I and I plus 1. Okay, so from xi minus 1 equation, we will eliminate or obtain what is the expression for xi minus 1. Okay, similarly from I plus 1, we will get an value for xi plus 1. Then substitute for that xi minus 1, xi plus 1 back into the ith equation. Okay, all right. So let us start off with I minus 1th equation. So what will be an equation for xi minus 1? Xi minus 1 will be equal to 1 upon bi minus 1, and then you have yi minus 1 minus ci minus 1 xi, and then minus ai minus 1 xi minus 2. Okay, that is straightforward. So basically it will be 1 by bi minus 1, you have yi minus 1 minus ci minus 1 xi minus ai minus 1 xi minus 2. Okay, all right, so that's your expression. Now what about xi plus 1 from the last equation? That's basically 1 by bi plus 1, you have yi plus 1 minus ci plus 1 xi plus 2 minus ai plus 1 xi. Okay, so that's your equation for xi plus 1. Now let us substitute for essentially your xi minus 1 in this equation here, and let us substitute for xi plus 1 in the equation for xi, ith equation for xi plus 1. Okay, now as you can clearly see that xi minus 1 now only contains xi and xi minus 2, and xi plus 1 contains xi and xi plus 2, and when we try to plug it in here, the resulting equation will only contain, as you can see, will only contain xi minus 2 and xi plus 2, right? Because we are now already eliminating xi minus 1 and xi plus 1 from these equations. So we have already removed the dependency on the neighbors, and we went to a dependency on further neighbors which are one cell or one neighbor away, right? That means if I substitute this into the equation for ith equation and kind of rearrange this, so I'm kind of skipping some algebra here, because you have to also kind of put this y minus 1 and y plus 1 to the right hand side. So I'm now defining with a superscript, so the resulting equation after substituting xi minus 1 and xi plus 1 into ith equation, okay? So basically, and doing some algebra, what we basically get is ai xi minus 2 plus bi xi plus ci xi plus 2 equals yi, okay? Now because this is the first step of the process or first iteration, I'm going to call this as with the superscript 1, okay? So this is ai1, bi1, ci1, where these superscripts kind of involve some coefficients which we got from here, okay? And also yi1, okay? So that is the equation. Now with these new coefficients, as ai1 is basically given by some alpha i1 times ai minus 1, okay? And then similarly bi1 is given by bi plus alpha i1 ci minus 1 plus beta i1 ai plus 1, and alpha and beta will also be given couple of with corresponding values. So ci1 is equal to beta i1 times ci plus 1, and then finally you have yi1s that are basically given by yi plus alpha i1 yi minus 1 plus beta i1 yi plus 1, okay? So we have some values for the new coefficients or the new coefficients in the system, and of course the values of alpha I will involve this coefficients, okay? This is basically minus a plus 1, a plus 1 by ba plus 1 minus ai minus 1 by ba minus 1, okay? So that is your coefficient is, okay, it basically is coming from here. So this is coefficient for alpha I1 is yeah, this ai divided by ba minus 1 and ci by ba plus 1, okay, because the minus ones are already written here, okay? So alpha I1 is basically given by minus ai by ba minus 1, and coefficient beta I is equal to minus ci by beta I plus 1, okay? So we have these two all these expressions, okay? Of course, with for the special cases of your 1, 2 and n minus 1 and n, which we did not do, you can kind of derive the corresponding formulae easily, right, following the same process. We don't have to do that because later on we will see to get the full equations, then you don't have to do that, okay? So essentially now we have got this new system, right? So this is a new system. Now how does the entries in this new system look like? Now what will be the corresponding matrix if I write a1 x, x should be the same, y1, right? If I write what is a x equals y with a and 1 have superscripts of 1, okay? So how does this system look like? This will look like basically a equals b1 of 1, and then the neighboring dependency is gone. You have c1 of 1 here, and then these are all zeros, right? And then you have 0 b2 of 1, 0 c2 of 1, right? And then in the third row you have a3 of 1, 0, b3 of 1, 0, c3 of 1. I think you're getting an idea of how it will be, right? So all the way like this, and then as you go down, right, you would basically get the final equation will contain bn of 1, 0, an of 1, right? And then everything else is 0 here and 0 here, okay? So we got a system in which the diagonals are now pushed one row away, right? For example, earlier they were here, now they were pushed out by one row, right? So these are all zeros. Okay, so essentially that means the diagonals are pushed one row away from the main diagonal. Okay, now the same thing can be repeated such that in the second step again they are pushed further, and then the dependency on for the ith equation or whatever, essentially your dependency on xi minus 2, xi plus 2 will be transformed into dependency on xi minus 4, xi plus 4 only, right? That means you can move, if you do another iteration, try to get these equations and then eliminate I minus 2, xi minus 2 from I minus 2 equation, and get an expression for xi plus 2 from I plus 2 equation, and substitute for xi minus 2 and xi plus 2 into the equation for xi. What you end up with is something known as an equation for I that contains xi minus 4 and xi plus 4. Okay, so if you do that, you get another matrix, that is the next iteration matrix, which I would like to write it as A2. A2 would look something like this. Okay, essentially you will get B1, but this we are giving a superscript 2 to differentiate that this is the next level of iterations, and then you would get 0 0 0 C1 of 2, and then you would get zeros all the way to 0. Okay, and then similarly you get 0 B2 of 2, 0 0 0 C2 of 2. Okay, essentially you will get 3 zeros, so they're basically pushed 1 2 3 4 fourth row or 3 rows away, right? And similarly you will get somewhere here 1 2 3, you would get this is basically 1 2 3 4, then you have A5 of 2, then you would get 1 2 how many zeros will be there? You would have 3 zeros, so 3 zeros, and then you would get B5 of 2, right? And then you will again get 1 2 3 zeros, you will get C5 of 2, right? And then you will have, of course, zeros here, right? And then finally the last row would contain Bn of 2, 0 0 0 An of 2. Okay, so what you see is that basically the diagonal elements are there, and then your off diagonal elements are now pushed by 3 more elements away, right, in both directions, in this direction as well as in this direction. So that is your kind of the recursive algorithm, and you keep doing that until your all these elements are kind of they will kind of go outside the matrix. Okay, so essentially you end up with only the diagonal elements. You only end up with the diagonal elements. Then once you have diagonal elements, you know that it is so easy to invert the matrix, right? You can just find the solution easily. Okay, so that is the idea. That means if I were to kind of write it, then what you basically have is you have the equation. So if I say we work with the equations, let's say at any step, let's say the kth step will work with equations of k minus 1 step, right? That means the k minus 1 step, the equations will be working with our with the I minus 2 to the k minus 1 ith equation and I plus 2 to the k minus 1. Okay, so we'll be working with these 3 equations, and once you eliminate, you're going to get the kth step equations, right? Okay, now what are these equations? That I minus 2k minus 1 I and I plus 2 to the power k minus 1, all these are in the superscript. Okay, k minus 1. Okay, all these equations are basically these 3 equations that the kth step will work with are a I minus 2 to the k minus 1. Okay, and then you would have x, we will see what is the subscript here, I would write it later, and b I minus 2 to the k minus 1, x I minus 2 to the k minus 1 plus c I minus 2 to the k minus 1, and then you would work with what will be this subscript here, because this is 2 to the k minus 1 away, so this you have to subtract minus 2 to the k minus 1 minus 2 to the k minus 1, right? So this will be so much away, so this is minus 2 to the 2 times 2k minus 1, that is basically 2 to the k, right? So this is basically I minus 2 to the k, and then on this side this will basically be xi, right? Because xi minus 2 to the k minus 1 plus 2 to the k minus 1, that will basically make it, the coefficient will be xi. Okay, and equals, on the right hand side you have yi minus 2 to the k minus 1, and all these of course have a superscript of k minus 1. Okay, I'm not writing it so that it will be easy, right? So we are basically working with the k minus 1 step, and similarly the ith equation will contain what? You would have ai bi xi, right? So I would just write it here. So you will get ai x, we will write the subscript later, so bi xi, and then plus ci xi plus 2 to the k minus 1, and this will be xi minus this should be xi minus 2 to the k minus 1. Okay, of course these are all to the power k minus 1 equals yi, right? That's your ith equation, and then your I plus 1th equation will be ai plus 2 to the k minus 1, right? Or not the I plus 1, the I plus 2 to the k minus 1 equation will be ai plus 2 to the k minus 1, x we will write the subscript later, plus bi plus 2 to the k minus 1, xi plus 2 to the k minus 1, plus ci plus 2 to the k minus 1. Then you have x, which should be 2 times this, so this will be xi plus 2k equals yi plus 2 to the k minus 1, and this will be 1 minus, right, I plus 2 to the minus a minus I, so this will be xi, right? Correct. Okay, so now what you do, you basically do write an equation for xi minus eliminate xi minus 2 to the k minus 1 from here, I plus 2 to the k minus 1 from here, and then substitute in here and here, and get an expression for in terms of xi minus 2k and xi plus 2k. That's all, right? Basically same as what we have done before, but with 2 to the power k substituted there, so it may look little complicated, but it's not very much complicated. Okay, so then in the kth step you will have after you eliminate these things, you will have the coefficients. Okay, essentially you end up with an equation, and that equation will contain xi minus 2, xi minus 2 to the power k, xi plus 2 to the power k, and then xi. So the resulting equation after elimination would read like this. You would get aik xi minus 2 to the k plus bik xi plus cik xi plus 2 to the k equals yik. Okay, you see the resemblance. So this is the kth step after applying the kth step equation, right? After eliminating these guys, right? After eliminating this and this from this equation and this equation, right? Okay, now of course we got these things. So what about the coefficients? Now that we have written the recursive formulae, let us see if we can write the final equations. So the final equations that you would need are ai to the k equals just like before, we'll have alpha I to the k, okay, and then you would have a to the power k minus 1. This to the power is basically indicates the particular iteration. Okay, it's not raised to the value, but it is just the iteration index, right? So and then you have ai minus 2 to the k minus 1. Okay, so this is valid for I equals 2 to the k plus 1 all the way to n, and aik equal to 0 otherwise. Okay, so only for these values of I it is given by this, otherwise it is 0. Similarly, we have to write ai, a, b, c and y formulae, and then of course later on we have to write for alpha and beta, just like we have done before. Okay, and then cik equals beta ik. You can derive all these things. Okay, I have, I'm just not doing the final derivation part. Ci plus 2 to the k minus 1 to the power k minus 1. Okay, so this is valid for I belongs to 1, 2 all the way to n minus 2 to the k. Okay, and cik equal to 0 otherwise. Okay, similarly bik equals, bik is the diagonal element, so diagonal element will belong you have alpha ik, ci minus 2 to the k minus 1, k minus 1, plus beta I k minus 1, okay, plus sorry, bi k minus 1, and then you have beta ik times ai plus 2 to the k minus 1 to the power k minus 1. Okay, so this is valid for I equals 1 to all the way to n for all of them. Of course, you need to have, right, because you end up with the diagonal matrix. And then finally the right hand side vector, that is yi to the k, is given by alpha I to the k, yi minus 2 to the k minus 1, k minus 1, and then you have plus yi k minus 1, plus you have beta I k, yi plus 2 to the k minus 1, and you have k minus 1. Okay, so that is also valid for all I equals 1 to all the way to n. Okay, that is fine. Now the only remaining things are your alpha ik and beta ik. So alpha ik is basically given by minus a k minus 1 I upon b k minus 1 I minus 2 to the k minus 1, and this is valid for I equals 2 to the k plus 1 all the way to n, just like the c of I. And then we have beta ik is basically given by minus ci k minus 1 divided by bi plus 2 to the k minus 1 k minus 1, and this is valid for I equals 1 to all the way to n minus 2 to the k minus 1. Okay, so with that essentially we complete all the coefficients that we need at any kth step. Okay, now once we have this, we can use these reconciliations to calculate all these expressions. Of course, we have to also initialize for k equal to 0. So for k equal to 0, the initialization of the values can be done as follows, right? Because we are using these relations. So ai of 0 can be initialized to ai for essentially I equals 2, 3 all the way to n. Similarly, bi of 0 can be taken as bi for I equals 1, 2 all the way to n. Similarly, for the c of I of 0 can be taken as c of I for I equals 1, 2 all the way to n minus 1. Similarly, yi of 0 can be taken as yi for essentially I equals 1 to all the way to n. Okay, so that is done. And of course you would also take a of 0, a1 of 0, right? a1 of 0 equal to 0. Similarly, cn of 0 equal to 0, because you know, when you allocate, you're going to allocate three arrays of uniform length. So as a result, you will just set them to 0. Now also you will initialize for all the steps of k goes from now 0, 1 all the way to, we are kind of doing this for a doubling exercise, so this will go all the way to log n iterations, and I would denote the if you get log n as a real number, you would round it off to the next integer, and then that is, we call it as an upper rounding, right? This is basically symbol for ceiling. Okay, all right. So, and then you would also initialize your at any step the values that you have, that is aik equals cik equals yik. At any step you will initialize with equal to 0, and then bik with 1 and xi with 0. Okay, so that's basically, with that, these recurrence relations should work to calculate the corresponding coefficients at any step. Okay, now basically once you initialize and then calculate these things, right? So after capital, let's say after log n steps, your matrix, original matrix A, will get transformed into new matrix A capital N, or A, you know, this will be log n, which I can write it as A cap, A to the power n, right? A super n. which is basically now be just a diagonal matrix, right? That means your an will look like a after log n iterations will look like b1 b1n b2n all the way to bnn, okay, and everything else is 0. Okay, this small n is little n is what we have, and capital N is equal to your ceiling value of log n, okay, after so many steps. All right, that's not too many. Okay, now once you have a of n and you also have a new y of n, then how would you calculate x? Calculation of x is super easy, because you can calculate xi equals yi of n by bi of n. That's all. So you just have to divide the right hand side vector with the corresponding diagonal element and then calculate. This is basically valid for I equals 1 to 3 all the way to n. Okay. Alright, so we were able to fortunately complete this whole exercise in one class. So let me kind of summarize. So what we do is basically in this recursive doubling process, we have two steps. One is the elimination step. In the elimination step, we compute a of ik, b of ik, c of cik, and yik for k equals 1, 2 all the way to log n, right? We calculate for these many steps, and for I equals 1, 2 all the way to n, and we do this we compute this according to these expressions, right? According to these expressions that we have. Okay, let me write these are equations A. Okay, these are equations A. Compute them according to equations A. Once we have them, then once you have those things, then you basically use a solution phase. In the solution phase, what we have is you can calculate what is xi equals yin by bin, right, for I equals 1, 2 all the way to n, and with capital N equals log little n, the upper limit. Okay, that's it. So we are able to calculate this. Now this algorithm is of course a lot more complicated or a lot more lengthy, as we discussed, but it's not too lengthy when you implement it. But as you can see, there are essentially n, there are basically log n loop here, and then in each log n you have n here. So as a result, the computational complexity of the serial computation complexity of the recursive doubling algorithm will come out to be n times log n, which is basically larger than the order n that we saw for the tridiagonal system, right, in a serial sense. Right, asymptotically this is larger than the order of n that we saw. But then what is the advantage of the second method, of the recursive doubling method? The advantage is that now the computations in each of the elimination and the solution phase, for example, once you are in this loop, the computations at any step k can be performed in parallel. Okay, and even in the solution phase. For example, if you look back at the equations, okay, now these equations, they all, the k values only depend on k minus 1, right? Once you compute alpha and beta, they only depend on k minus 1 everywhere. So as a result, you can compute the k values all in a, and then not only k minus 1 values, of course that's not the whole point, because that is anyway running in the same loop. Your I values only depend on I minus 2, I, and so on. So as a result, these are all available, right? So at the previous values. Okay, so as a result, there is no data dependency or loop carry dependency in a sense that it can affect the performance, okay, or the result. So as a result, basically your elimination and solution phase can be performed in solution, they are independent and then can be performed in parallel at any step k. Okay, so that is the whole idea of the recursive doubling algorithm. So hopefully in parallel, although this is this is little larger, it will kind of run faster compared to your serial version of the Gaussian elimination. Okay, so of course there is also a little bit increase in memory, because now we will also allocate values for AIK, BIK, CIK for each of the steps, right? So there is an increase in memory as well. But this is one of the algorithms that is used in the computations when it comes to parallel solving for parallel tridiagonal matrices or systems. Okay. All right. So far so good. I'm going to stop here. We will catch up from here in the next lecture. Okay. Thank you.